In the beginning of this chapter, we learned that the molecules which have the same molecular formula but different structural formula are known as isomers. The examples of these compounds uh, can be written such as these two compounds. Both of these compounds have a molecular formula of C4H10. However, we can clearly see that both of their structures are totally different. So these kind of compounds are isomers of each other. Now, isomers can be subdivided into two categories. So one category is known as constitutional isomers. These are the types which we defined earlier, and this is the example which I wrote earlier is an example of constitutional isomer. So constitutional isomers are different compounds with same molecular formula but different connectivity. And as we can see that in this case, the methyl group connectivity is different than the other compound. Now in this section, we are going to introduce the concept of stereoisomerism. Stereoisomers are compounds that have the same molecular formula as in the case of other one. At the same time, the connectivity of the atoms is also same. Only thing different is the orientation of their atoms in space. So we can define stereoisomers as those compounds which have same molecular formula, same connectivity, but different orientation of their atoms in space. The example of stereoisomerism can be expressed as this one. For example, if we have a compound where cyclohexane has two methyl substituent, one above the plane and other below the plane, and in the second compound both methyl groups are above the plane. These two are stereoisomers of each other. Why? Because the molecular formula is same, connectivity is same, only difference is the orientation in the space. So in one case, the methyl group is oriented differently than the other. We will study stereoisomers in detail in chapter number 3. In this section, we will only focus on one section of stereoisomers, which are known as cis-trans isomers. Cis-trans isomers are those stereoisomers that are the result of relative orientation of groups bound either to a ring, which we will study in this chapter, or to a carbon-carbon double bond, and this kind of cis-trans isomerism will be studied in chapter number 5. To give you a short definition, so if we have an example of a ring and both substituents are on the same side, then and we have similar molecule where substituents are on the opposite side. So in this case they are same side above the plane. In this case one is above, the other one is below. So the same side isomer is known as cis isomer, the other one is known as trans isomer. The cis-trans isomers of 1,2-dimethylcyclopentane molecule are shown here. As we can see that in the first case both methyl groups are on the same side of the molecule, that is both of these substituents are below the plane of the ring. So therefore this isomer is known as cis isomer. In the structure on the right, the methyl groups are on the opposite sides of the plane, so therefore this is known as trans isomer. Cis and trans isomers are denoted by putting a prefix cis or trans in front of the name. The prefix cis indicates the substituent are on the same side. Cis is derived from Latin word which means the same side, and trans is derived from a Latin word which means across. We also use the dashed and wedge bonds to indicate whether the substituents are above the plane or below the plane. The wedge bond, this bond means that the substituent is coming towards you or out of the plane, and the dashed bond means that the substituent is away from you or behind the plane. And this bond means above the plane. So if one bond is above the plane, the other one is behind the plane, then of course the molecule is a trans isomer. If both bonds are behind the plane, then it's a cis. Also, if both bonds are above the plane, for example, this way, this will also be a cis isomer. One thing should be noted that the cis isomer cannot be converted into trans isomers or vice versa by simple rotation of carbon-carbon bonds. In order to convert cis to trans, we either have to break or reform one or more bond, and this kind of process does not occur at room temperature or by itself. So therefore we can safely say that cis isomers cannot be converted into trans isomers by itself. On the contrary, conformations can be converted from one to another conformation. For example, staggered conformation can be converted into eclipse one. So that's the main difference between stereoisomers and conformations. Another thing should be noted here is that cis isomer is approximately 7.1 kilojoules per mole higher in energy than trans. In other words, trans isomer is more stable. This difference in stability can be attributed to the steric strain caused by the substituent group on the same side in case of cis stereoisomer. The atom, most commonly the carbon atom, about which exchange of two groups produces a different stereoisomer is known as stereocenter. For example, in case of dimethyl 1,2-dimethyl cyclopentane or cyclobutane, these two carbon atoms are stereocenters because the exchange of substituent about these two carbon atoms will produce a stereoisomer. Configuration refers to the arrangement of atoms about a stereocenter. So for example, we can say that the exchange of groups at either stereocenter, either here or here, will produce another stereoisomer. So let's check the cis-trans isomers of 1,4-dimethyl cyclohexane. The structure on the left hand side, we can see that one of the methyl group is above the plane, the other one is below the plane, so they are across from each other, hence this conformation is trans. In this example structure on the right hand side, both methyl groups are on the same side, which is below the plane, hence this configuration is cis. These isomers can also be represented with the use of dash and wedge bond. So dash bond means below the plane and the wedge means above the plane, in both cases, it will remain the trans isomer. Similarly, a chair conformation uh, is also used to show the cis trans. In this case, if we represent this as imaginary plane of the ring, then we can see that one of the methyl group is above the plane, the other methyl group is below the plane, hence it's also a trans. So all three structures represent the same molecule. Similarly, structures on the right hand side show a cis isomer structure. One thing to note here is that in case of trans isomers, both of these methyl groups occupy equatorial position. That's the more stable orientation. In case of cis, uh, this methyl group is equatorial. However, the other one is axial. And we know that axial position is not stable because of 1,3 steric strain, and therefore that also confirms why the cis isomer is relatively unstable. It's not unstable, but slightly higher in energy as compared to the trans isomer. Earlier we learned that if we have a cyclohexane, the chair form is in equilibrium where in two different conformations, and the probability of having in these two conformation is exactly the same. So 50% in one conformation and 50% in the other conformation. However, if we have a substituent attached, then the equilibrium will not be 50-50. So we learned earlier that if there is a substituent connected to either 1 or 4 position, so for example here, if we have a methyl group and when it flips, the axial methyl group become equatorial. In that case, the conformation where the substituent group is on equatorial position, that equilibrium will shift towards that side, and this will be the major conformation. The other one will be minor. Now let's take a look at example of 1,4-dimethyl cyclohexene. So in this case, again, as we learned previously, that the substituent groups do prefer equatorial position. So if we have substituent group as an on axial position, so when the chair flips and undergoes to form the other conformation, so the axial positions will become equatorial position. We know that axial positions are not stable because of because there is an interaction between 1,3 diaxial interactions. So these steric interactions make it unstable. Similarly, this group will have interaction with these axial hydrogens. So these 1,3 diaxial interactions make this conformation less stable. I should say less stable. On the other hand, the equatorial position, so no steric strain exists. So no steric strain. So this is more stable. So hence the equilibrium will not be shifted equally. So in this case, the preferred orientation will be, or preferred conformation will be the one on the right hand side. So in other words, the di-equatorial methyl chair conformation is more stable, and the calculated energy of stabilization is about 14.56 kilojoules per mole. The 1,3-diaxial interaction can be better visualized with the ball and stick model, where the axial carbon or methyl group can easily be seen super close to the methyl groups on these carbons. So these are 1,3-diaxial interaction. These are actually the repulsive forces, although it's a interaction, they make the molecules unstable. No such interaction occurs in the equatorial position methyl groups, so therefore the diequatorial cyclohexane is more stable. In case of cis-1,4-dimethylcyclohexane, both conformations are equally uh, probable, because in each case one methyl group will be axial, the other one will be equatorial. So it doesn't matter whether it's on in the left side conformation or the right side conformation, they will have equal 1,3-diaxial interaction. So hence both of these conformations are equal, have equal probability, they are equal stability. Out of all the bicyclo compounds, we will mainly focus on the decalenes and hydrandanes in this chapter. Decalene is a bicyclo compound in which we can say the two 6-membered rings are fused with each other. In hydrandane, a 6-membered ring is fused with a 5-membered ring, but the cis-trans isomer pattern is similar in both the cases. The two stereoisomers of decalene and hydrandane are possible depending on whether the two hydrogen atoms at the bridge carbons, as shown here, are both present on the same side of the ring plane, or if they are present on the opposite side, as shown here. In the trans, as we understand that the hydrogens has to be across from each other. So in case of decalenes, we mainly consider the hydrogens on the bridging carbons. If they are across, then it's a trans isomer. The ball and stick model of trans decalene is shown here, and if they are in the same side, then it's called cis isomer, and the ball and stick model of cis decalene is also shown here. If we draw the conformation of decalenes as shown here, we will see that each ring can exist in its most stable chair conformation. So although there are two rings fused together, but both of those rings are in chair conformation in both trans as well as cis isomer. In transdecalene, the hydrogens in the ring junction, these hydrogens, both of these hydrogens are at axial position. That is, the ring junction hydrogen above the plane and below the plane, both of them are axial position to the ring, both rings. On the other hand, if we look at the cis decalene, we'll see that this hydrogen is trans to ring number B, and this hydrogen is trans to ring number A. However, both of these hydrogen, sorry, let me rephrase it. So in case of cis decalene, this hydrogen is axial to ring number B, and this hydrogen is axial to ring number A. However, this hydrogen is at equatorial position to A, and the other hydrogen is equatorial position to B. So in other words, in cis decalene, each hydrogen is axial to one ring but equatorial to the other ring. Therefore, as we understand that equatorial positions are relatively stable as compared to axial position, hence the cis isomer is uh, more stable. A good example of occurrence of cis-trans isomers of bicyclo-ring compounds can be found in steroids. All steroids consist of three 6-membered cyclic rings and a 5-membered cyclic ring, and this um, parent structure is known as steroid nucleus. This kind of steroid nucleus is present in both animal as well as plant steroids. Steroids are present in human metabolism as cholesterol, steroid hormones, and bile acids. The structure of cholesterol is shown here, and as we can see that many cis-trans stereoisomers are possible in these systems. Another type of bicycloalkane is a 6-member ring in which the number 1 carbon and number 4 carbon are connected with a bridge. This kind of cycloalkane or bicycloalkane can be viewed in many different perspectives. For example, if we view from the side, the molecule will appear as a structure shown in B. And another perspective is the structure shown in C. So all of these A, B, and C are same molecule viewed from different perspectives. One thing we should note here is that although A and B are shown from different perspective, but it is not clear. The more clear picture appears when we see this molecule from the perspective as shown in C. In this perspective, we can see here is that this molecule is locked permanently in boat conformation. Because of the bridge, this boat conformation cannot go to chair conformation, and it stays as a boat permanently. The lesson here is that it is essential to draw a molecule as a three-dimensional shape which is best for the purpose you want to show. Camphor is a good example of these kind of molecules. Camphor is a naturally occurring compound, and it has uh, this kind of structure. That the common name for this kind of structure is norborane. Another example of a carbon skeleton that contains several 6-member rings, and all of which are locked into chair conformation. A chair conformation of cyclohexane is shown here, and if we draw three axial bonds, and all of these axial bonds are connected with a common CH group here, so now this bridge or tri-bridge, I would say, locks this chair conformation in permanent chair. Because of the presence of this locked bridge, this chair conformation cannot switch to the board or the other chair. The compounds with this kind of structure are known as adamantane, and adamantanes were first discovered during the refining process of petroleum. Amantadine is an example of molecule. It's a derivative of adamantane, and this compound has been found to be antiviral agent, and it is used to treat influenza A. We will now discuss physical properties of alkane. Now, because alkanes are a class of hydrocarbons, that means that they are made up of only carbon and hydrogen. And we have learned previously that carbon and hydrogen have almost similar electronegativity. So therefore, one of the most important property of alkanes and cycloalkanes is their almost complete lack of polarity. The bonds between carbon and hydrogen, such as in methane, they have electronegativity difference of 0.4. And according to Pauling scale, these bonds are categorized as pure covalent bonds. It means they do not have any polarity. Due to complete lack of polarity, the only intermolecular force which exists in alkanes is London dispersion force. To review different kind of intermolecular forces, we know that there are ion-ion intermolecular forces. These are electrostatic interactions which exist in positive ions and negative ions, such as sodium ion and chloride ion. These kind of forces exist in ionic compounds. Ion dipole kind of interaction exists when we dissolve ionic compound in a polar solvent, such as sodium chloride in water. In polar covalent compounds, we may find dipole-dipole interaction or hydrogen bonding. In dipole-dipole interactions, uh, uh, dipole-dipole interactions exist in those covalent molecules who have polar covalent bonds, and hydrogen bonding exists in those covalent molecules where hydrogen is connected to either oxygen, nitrogen, or fluorine. In alkanes, none of these three interactions exist. Only interaction which exists in alkanes is London dispersion force. London dispersion force is extremely weak electrostatic interaction which arises due to a temporary shift of electron cloud in the molecule. For example, in case of a neon atom, temporarily if the electron cloud shifts to one side, that side becomes negative, the other side becomes positive. So that will create a temporary dipole, and this temporary dipole will generate a temporary dipole in the neighboring atom, and resulting temporary electrostatic attraction will be categorized as London dispersion force, or simply dispersion force. One thing we should remember is that this dispersion force is extremely weak and it's temporary. The existence of only dispersion force accounts for the fact that low molecular weight alkanes are gases at room temperature. The strength of dispersion force depends on how easily an electron cloud can be polarized. Polarized means it can be shifted to one side over the other. And electrons in smaller atoms and molecules are held closer to their nuclei, so therefore they cannot be shifted to one side over the other. For example, if we have a tiny atom and it has electrons, so both of those electrons are held closer and they cannot be shifted to one side. But if we have a larger atom and it has bunch of electrons, it's quite likely that electrons can be temporarily shifted to one side over the other, so resulting in one side being electronegatively rich, or in other words delta negative, and the other side would be delta positive. So this is said to be the condition in which atom is more polarizable. So more polarizable means that the other atom will also behave in such a way that it will create a relatively larger or stronger dipole-dipole interaction. So in other words, we can say that the extent of dispersion force depends on the size. In general, larger molecules have a higher polarizability, resulting in stronger interaction. Therefore, higher molecular weight alkanes are liquids, and if we go even more higher molecular weight alkanes, they tend to be semi-solids or solids. Solids means that they have a stronger intermolecular force as compared to gases. That are constitutional isomers have different uh, physical and chemical properties. This table lists some of the physical properties of various constitutional isomers of hexane, and we can see that the melting point and boiling points are different from each other, as well as the densities are also different. All of these molecules have same molecular formula, which is C6 and H14. However, their physical and chemical properties are completely different from each other. There are few important generalizations we can make from this table. The first key generalization is that the boiling point of each of the branched isomer is lower than that of linear hexane. For example, 2-methylpentane is negative 154 and hexane is negative 95. Also, another thing to be noted here is that the boiling point of each of the branch chain isomer uh, is more lower if there is more branching. For example, 3-methylpentane has only one branch and its melting point is negative 118, and 2,3-dimethylbutane has two branch and its melting point is lower than that of single branch. These differences in boiling point are related to molecular shape in such a way that that as the branching increases, the shape of an alkane molecule becomes more compact, and hence its surface area decreases. And with decrease in surface area, the London dispersion force will also decrease, and if the London dispersion force decreases, hence the melting and boiling points will also decrease. So we can say more branching will lead to compact surface. Compact surface means smaller size. Smaller size means smaller dispersion force. And we already know that if the dispersion force decreases, the melting and boiling points will also decrease. Let's discuss chemical properties of alkanes and cycloalkanes. Uh, both alkanes and cycloalkanes are quite unreactive towards most reagents. The reason is that all the bonds in alkanes and cycloalkanes are sigma bonds, which are relatively quite strong bonds. Also, all the bonds are non-polar. So, under these conditions, alkanes and cycloalkanes do not react with most of the lab reagents. One of the very few reactions which alkanes and cycloalkanes do give is oxidation. In oxidation of alkanes, they react with oxygen, and this reaction is exothermic, and products of this reaction are carbon dioxide and water. Oxidation of alkanes is by far the most important reaction of alkanes, economically speaking, because that's where the energy needs of our society are met. Most of the energy is produced by combustion of alkanes. Couple of examples of oxidation of alkanes such as methane and propane are given here. As you can see that regardless of uh, what alkane we start with, the products are always the same. In the oxidation reaction of alkanes, the energy of products is much less than the energy of starting compound alkanes. Therefore, all of these reactions release a lot of uh, excess energy, and that energy is known as heat of combustion. Heat of combustion of a few of the common alkanes are listed here, and we can see from this table that alkanes release quite a bit uh, of energy. This table lists the heat of combustion of constitutional isomers of octane. By inspecting the values, we can see that as the branching are going up, for example, in this case we have only one branch, two branch, and then eventually we have four branch. As the number of branches are going up, the energy release is going down, so less energy. So in other words, more branching means that the compound is more stable. Because the compound was more stable, hence it released less energy. Therefore, heat of combustion can be used to determine the stability of various isomers of alkanes or constitutional isomers of alkanes. So we can generalize that smaller the heat of combustion from any isomer, more stable that isomer is. And from that, we can also calculate the difference between the energy of one isomer to the other. It has been determined by measurement of heat of combustions of series of unbranched alkanes. For example, methane and then ethane, propane, butane, and so on. So when we measure the heat of combustion and analyze the results, we found that for each CH2 group present in a molecule, the molecule will release 658.7 kilojoules of energy. So in other words, if we have a ring with 6 CH2s, so theoretically this should release 6 times 658.7 kilojoules of energy. That's theoretical. And experimentally we can burn it and we'll see how much energy it does release. And it was found that in case of hexane, as shown here, the theoretical energy and the experimental energy were exactly the same. So the difference between the theoretical heat of combustion and experimental was zero because they were same. So that's why it is zero for this one. All other ring systems, they experimentally release more energy than what was theoretically calculated. That extra amount of energy which was released is attributed to the strain in the ring system. And as we can see that the ring systems with 3 carbon and 4 carbon possess a lot of strain. So with this calculation we can figure out the amount of strain present in any ring system. And we can see that the rings with 6 carbon or 14 carbon do not possess any strain. All other rings do possess some strain energy. Alkanes are sourced from fossil fuels. And the three main sources of alkanes are natural gas, petroleum, and coal. Fossil fuels are major source of energy in United States and in rest of the world, although renewable sources such as solar, wind, and nuclear uh, are becoming more and more popular because of harmful environmental effects of fossil fuels. Natural gas consists of approximately 90 to 95% methane and about 5 to 10% ethane. And maybe some traces of some other low boiling alkanes. Petroleum is a thick, viscous, oily uh, liquid which is a mixture of thousands of compounds, and most of those compounds are hydrocarbons. Petroleum is formed or was formed from the decomposition of marine plants and animals. Petroleum and petroleum derived products fuel automobiles, aircrafts, and other vehicles. They also provide most of the lubricant required for many machinery. And furthermore, petroleum along with natural gas provide nearly 90% of organic raw material for synthesis and manufacturing of synthetic fibers, plastics, drugs, detergents, dyes, and multitude of other products. In crude form, petroleum does not have many uses. So petroleum undergoes a process of refining, and after the refining is done, multitude of compounds are obtained, and uh, uh, those products are collected based on their boiling point or the temperature where the refining is done. So below 20 degrees Celsius, gases are obtained, and these gases are propane, butane, or ethane. Between 20 to 200 degrees Celsius, liquids, which are also known as naphthas, are collected. In this zone, gasoline, diesel, and few other liquid fuels are collected. Kerosene is collected between 175 to 275 degree, and at higher temperature, we collect fuel oil, lubricating oil, and asphalt. Although coal is just pure carbon, but coal can also be a source of hydrocarbon. So one of the important reaction by which coal can be a source of hydrocarbon is known as synthesis gas production. Now, we must understand what is synthesis gas to begin with. So when steam is passed over a burning red hot coal, so this reaction takes place at high temperature. The products of this reaction are carbon monoxide and hydrogen. This mixture is known as synthesis gas. Synthesis gas with the help of some catalyst can be converted into various kind of hydrocarbons. The first product will be methanol, and from methanol multitude of other organic compounds can be generated. The refining of petroleum is carried out in a process called fractional distillation of petroleum. In briefly speaking, fractional distillation of petroleum is done in a large column kind of equipment, and in this process the crude oil and vapors are preheated, and the vapors of crude oil are are um, are entered in the distillation column. Now, distillation column is set in such a way that as we go up in the distillation column, temperature decreases. So when these vapors go inside, because these vapors contain thousands and thousands of different kind of hydrocarbons, many of them have low boiling point, so they will stay as vapor, so they will rise up. And some of them who have high boiling point, they will immediately liquefy. And when they liquefy, so those the ones which liquefy, they get collected in this zone, and this zone is whatever we collect in this zone is called lubricating oil. The vapors which go up, as they move up, because temperature decreases, some of them will liquefy at the first collection zone, and all the products which are collected in this zone are fuel oil, and remaining vapors will go further up, and kerosene oil uh, distillates or liquefies between this temperature zone and is collected here. And then further up, temperature cools down more, and then more fractions are collected, and the fractions which are collected here are naphthas, which is gasoline. And the remaining vapors which do not liquefy or do not get distillate, they remain as gases, so they are collected from the top. So these are the gases such as methane, butane, or ethane. Synthesis gas is obtained when a steam is passed over a red hot coal, and it results in a mixture of carbon monoxide and hydrogen. Synthesis gas by itself can be used as a fuel because it burns. However, presence of carbon monoxide, which is toxic in nature, makes this fuel not desirable. Synthesis gas can also be produced catalytically by reacting methane with oxygen in presence of catalyst, and resulting mixture is again a synthesis gas. Now, synthesis gas is one of the important precursor because it can react with a catalyst, or in presence of a catalyst, it results in formation of methanol. Methanol is one of the important starting organic compound because methanol can be converted into acetic acid, and from acetic acid more organic compounds can be synthesized. With that, we conclude chapter number 2. In this chapter, we learned about alkanes and cycloalkanes. We learned about their nomenclature, their structures, their conformations, as well as their physical and chemical properties. Thank you everyone for watching the video, and if you have any question and concern, please let me know. Thank you.